Welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen, and we're continuing our talk onto Inference Part 3, wrapping up our whole introduction to the inference discussion space. And in the 7.1 video, we talked about the few different distributions you might encounter in this course. We're going to be introducing other ones as we get to those specific tests. Like you learned about the chi-square distribution when we did the chi-square tests. And we introduced a few other ones like the uniform and the Bernoulli in the previous video. In this one, we're going to start talking about the normal distribution and a few other elements for it. So let's go ahead and get started with talks on normal distributions and introducing this concept we call z-scores. Now, when we're talking about numerical data, we're talking about how we can plot it, we can shape it, and how we can look at the different summary statistics to give us some sort of insight about the data. That's when we're talking about things like its mean and its median, its standard deviation, its IQR, all sorts of different metrics like these. Now, when we plot these out, we can talk about them in terms of their skew. Are they left skewed? Are they right skewed? And when they're skewed, we use things like the median and the IQR to talk about its center and spread because they're more robust. They're not going to be pulled off or they're going to be less resistant to being pulled off into one of the particular tails, unlike the mean and standard deviation. However, for symmetrical distributions that do not have a long tail in either direction, we can go ahead and use the mean and standard deviation to describe the spread because they're not going to have to be worried about being pulled in any particular direction. So let's talk a little bit more about unimodal symmetrical spreads. Now, we say unimodal symmetrical distributions, they're special in our case because of these different characteristics that they don't have tails and things like this. So we can go ahead and use means and standard deviations for more information. Means and standard deviations tend to be more precise, and we can use these to do all sorts of inferential tests to get very approximate answers. And so when we're dealing with this particular type of curve, it's called the normal distribution. Now, characteristics of a theoretical normal distribution are, first of all, that it's bell-shaped. If you've ever seen a big bell, those things that hang up in like church towers or small little doors and galleys that go ding ding, that's the old classic bell, not necessarily a digital one you might find on your phone. And they're unimodal. So unimodal meaning it only has one hump. It's symmetrical, meaning if we were to fold it in half on a vertical line chopping through it, it's going to pretty much overlap each other very nicely. It's unskewed, which means it doesn't have a tail one way or the other. And the mean, the median, the mode are approximately the same. Well, it's not approximately, they are the same value. And a lot of these characteristics go into each other. So in this case, because it's unskewed, it can also be symmetrical. And because it's bell-shaped, it can also be symmetrical. If it had this weird wobble to it or it had a tail, then these characteristics would be different from each other. And the mean, the median, the mode are only going to overlap when we have a curve that is symmetrical, unskewed, bell-shaped, etc. Now let's talk a little bit about the characteristics as well about normal distributions. So we talk about them in terms of means and standard deviations, and I want to introduce you to a few notation values here. So if I ever say put something in symbol form, these are some of the symbols that I'm going to be referring that you use. So the mean is characterized by the Greek letter mu, which kind of looks like a U with a little tail hanging off the front. Standard deviation is characterized by the Greek letter sigma, and looks like the O with a little tail hanging off the top. Think of it like almost like a little hat. And if we're talking about the normal distribution with a mean of U and a standard deviation of sigma, we characterize that by a capital N, open parentheses, mu, semicolon, sigma. And we can also replace those with particular numbers to say that we have a normal distribution with whichever mean value we have, and then whichever standard deviation value we have. Now, distributions they don't always look the same. They are all symmetrical, they're all bell-shaped, they're all means, median, modes are the same. They have the same base characteristics, but in terms of their overall shape, some of them are tall and spiky, some of them are short and flat and look just like a little mound compared to the Mount Everest peaks, and others are a nice medium in between. All of these are normal distributions, and we're not going to get heavily into these, but when we talked about skew, meaning you could have a tail out to the left or the right, we have other types of skew that we can talk about in terms of how tall is it and how flat is it, and these are things that we could call, I got to get my language here straight, platykurtic and leptokurtic, if I'm remembering correctly, but that's a little above what we're going to be worrying about in this particular course. But either way, for generally what we're doing, the normal distribution, we're not going to worry about how tall or flat it is, but the characteristics we're going to be talking about at them will apply no matter how tall or how flat it is. Now keep in mind, some distributions may seem normal, but they're not always. And this is because when we're getting to real life. A lot of things that we're looking at, you're going to plot it out, and you're going to say, ooh, this isn't quite normal. But that's because a lot of things in life are rarely normal. But we use normal distributions to approximate these instances because they can be very informative. And as we're going to learn when we get to central limit theorem, some of the inconsistencies that we see where things aren't quite normal aren't going to matter anyways because of the central limit theorem. So what kind of information does the normal distribution give us? Well, it gives us the empirical rule, or also known as the 60-95-98 rule. And what this says is that under a normal distribution, we can identify what proportion of the sample or the population is going to exist under that curve. And so we take the center of the normal distribution, and that's mu, or if it's standardized, 0. And we can go out one standard deviation in either direction. That's plus or minus one standard deviation. And we know that since it has all of these characteristics like symmetrical and bell-shaped and mean, median, the mode are the same, etc., we know that 68% of all possible values under the normal curve are going to live within plus or minus one standard deviation. Going out a little bit farther to plus or minus 2 standard deviations, 95% of all observations live within plus or minus 2. And within plus or minus 3, we hit 99%, or 99.7 if we want to go a little bit more approximate into the decimal ranges here. Now, if you've ever heard of 6 sigma, it's a common term used in process manufacturing and quality control improvement systems. What they're talking about is making sure that their quality metrics are within plus or minus 3 standard deviations of each other, or 6 sigmas, 3 to the left and 3 to the right. And that says that their quality products are going to be within 99.7% quality metrics acceptable. And then outside of that is where they're going to look for additional improvements and things that control. But going back to our empirical rule here, we can look at this a little bit farther and say, because the normal curve is split in half with half positives and half negatives under there, we can break out our percentages a little bit more. So that 68%, which is 68.2, and there is a longer decimal to this, I've rounded for sake of simplicity here. 68.2 is within plus or minus 1 standard deviation. But from 0 to negative 1 standard deviation is 34.1%, and to 0 to positive 1 standard deviation is 34.1% as well. And we can break out a little bit more. From negative 1 to negative 2 is about 13.6% of the curve. From positive 1 to positive 2, another 13.6% of the curve. Summed together, we get across from negative 2 to plus 2 standard deviations, 95.4%. I think you hopefully might get the idea at this point. And keeping in mind, these percentages come from the fact that all possible values come from under the curve. And there's a 100% space under the curve. And so we can use math to figure out what the probabilities are at any given point under the curve. So let's see then how we can go ahead and take some of the values you might get from actual data and compare it to normal distributions. Let's use for a case example that you're looking at the statistics class we're in, and we could use a midterm perhaps from a previous term. On the first midterm exam, the scores were approximately normal with a mean of 60 and a standard deviation of 6. On the second midterm exam, we could say that these scores had a mean of 80 and a standard deviation of 4. And so what I want to know, and they're on the plot here on the screen, the first one is in green, the second one is in red. Actually, I think I've got my flags there a little bit backwards. I think the red one's supposed to be the first midterm and the green one's supposed to be second. But what we're generally going to ask is, if you got a score of a 68 on the first midterm and you got an 86 on the second midterm, which one did you do better on relatively? And to answer this question, we need a concept called z-scores, which I'm going to introduce to you in the next video. I'll see you then.